This lesson is intended to address a point that I made in the previous lesson, and that's the fact that surds are irrational. When we first introduced surds, we spent most of our time focusing on the number, the square root of 2. We said that we can approximate the square root of 2 as a series of rational decimals. So for example, we can write the square root of 2 as 1.41 and then a whole bunch of other digits. This approximation to the square root of 2, which is 1.414213562373009, is really just an approximation. You can continue this process for as long as you like, but you'll never actually have the exact square root of 2. You would need an infinite number of digits to ever do that, and as we said, that's absurd. But there is one really big difference between the square root of 2 and a rational number, and that's the fact that the square root of 2 is irrational. We hinted at this in the previous lesson, but the whole idea is that an irrational number is just a number that is not rational. So then the real question is, how do we know when a number is irrational, and how can we prove that the square root of 2 is actually irrational? Now this set Q contains all of the rational numbers, and therefore, outside of it, we have this set that we call the real numbers. And we want to show that the square root of 2 does not belong inside this set. To show that the square root of 2 does not belong inside this set, we have to be very clear about what allows a number to belong to this set. For a number to be rational, there are two ways that you can think about it. It must be possible to write the number as an integer divided by another integer. So for example, this number is 17 divided by 26, and both of those are integers. Now, another way that you can actually identify a rational number is by looking at the decimals of that rational number. If we rewrote 17 over 26 as a decimal, it would be equal to 0.6538461538461, and so on. Now, for any rational number, you're always going to see this occurring. I want you to see that this 538461 just keeps repeating over and over and over again. Because these digits are being repeated over and over again, then we don't really need any of the digits that come after it. Now, because there are 6 digits being repeated, we would say that the period of this rational number is 6. But there's nothing special about the number 6, and different rational numbers will actually have totally different periods. So, for example, this number over here is still a rational number because it's an integer divided by another integer. But if we wrote out the decimal expansion, then you'll notice something a little bit different. Upon expanding the digits of this particular fraction, we can see that it equals 0.58644, and then we'd keep going for a really long time. It turns out that the period of this particular fraction is actually 58, so you would need 58 digits after this 8 to get back to the 8 one more time. Now 58 digits is a whole lot of digits, but eventually we get back there. So the real question we're asking is, how do we know that the square root of 2 doesn't also have the same property? How do we know that if we kept writing out digits, we would never see the digits starting to repeat again? So we can say that anything that belongs to this set of rational numbers must have a finite period. It can be a really large period, but it must be finite. Even if it's something like 58, that is still a finite number. So therefore, if a number does not belong inside the set of rational numbers, then it must not have a finite period. And the claim we're making is that the square root of 2 does not have a finite period. So you could keep writing out digits for the rest of eternity, and you would never see the digits starting to repeat, ever. So the whole point I'd like to make beyond this point is that the square root of 2 is not a rational number. So therefore it is irrational, or it has no finite period. You'd have to keep writing out digits for the rest of eternity, and you would never see a pattern. So we want to conclusively show that the square root of 2 actually belongs over here, and it does not belong inside the blue set. Now the way we're going to go about doing that is we're going to try actually writing it as a rational number, where we write a over b, where a and b are two integers, and those two integers cannot have any common factors. So we want to try writing the square root of 2 as a rational number, where a and b are two coprime integers. Now I'm going to explain what coprime means in a minute, but the whole idea is that we want to find a and b that makes this whole equation true. Now to explain this further, we know that the square root of 2 is approximately equal to 1.4. if we ignore all of the rest of the digits. And then we can also say that 1.4 is the same thing as 14 over 10. Now, whilst 14 on 10 is a good approximation to the square root of 2, they are not equal, so that's why I've written this squiggly line here, which means that the square root of 2 approximates 14 on 10. Now, if this is the case, I want you to realize that 14 on 10 is not actually its simplest form. Because we can write 14 as 7 times 2, and we can write 10 as 5 times 2, we can cross out the 2's to come up with a simpler fraction. So if 14 is 7 times 2, and 10 is 5 times 2, these 2's can go away, and you're left with 7 on 5. Now in this case, the a on the top is the same thing as 7, and the b on the bottom is the same thing as 5. So we can say that the square root of 2 is approximately equal to 7 on 5, but they're definitely not equal to each other. So the whole idea is that if we want the left-hand side to be equal to the right-hand side, we have to find two different numbers, a and b, that will make the left actually equal to the right. Well, you can sit there and try as many numbers as you like, but what we're going to try to do is we're going to try to actually rewrite this in a way that helps us find the values of a and b. But before we move on, I just need to point out the fact again that we're going to need to use for this proof. We know that a and b need to be two co-prime integers. So for example, if a was 14 and b was 10, then that wouldn't work because you could simplify this to 7 on 5. So we'd like to find the values a and b that make the right-hand side completely equal to the left-hand side. We don't want to be approximately equal, we want to be exactly equal. So if we know that the square root of 2 is equal to a over b, then if we square both sides, we can rewrite this as the square root of 2 squared, which is equal to a over b all squared. Using the fact that the square root of 2 is the same thing as 2 to the power of 1/2, we can go ahead and replace this. And then, by using the index laws, we can multiply this 1/2 and this 2 to end up with 2 to the power of 1. And of course, if you have 2 to the power of 1, you really don't need to write that 1, so let me just get rid of it. If we also use the index laws on the right-hand side, we can also rewrite this as a squared all over b squared, so we can move the squared into both of these. So that means if the square root of 2 equals a over b squared, then that is totally equivalent to 2 equals a squared over b squared. But we can actually simplify this even further by multiplying both sides of this equation by this b squared over here. When we do this, the b squareds on the right-hand side actually end up crossing each other out, so we can get rid of them to write 2b squared equals a squared. Now, despite the fact that this expression is totally the same as this expression up here, writing it in this form actually allows us to see something really important. I want you to look carefully at the left-hand side. On the left-hand side, we're multiplying the number 2 by the number b squared. Now, if you multiply any number by the number 2, it must be an even number. And that means 2b squared has to be an even number. Now, if 2b squared is going to be an even number, and the left is exactly equal to the right, then if the left is even, the right must also be even. And that means a squared must also be an even number. Now, if a squared is going to be an even number, there's actually something else we can also say about the value of a. To explain this to you, I'm going to compare the squares of two different integers. Now, I want to compare the value you get when you square the number 2, which is 2 times 2, and the value you get when you square the number 3, which is 3 times 3. We know that 2 times 2 is the same thing as 4, and 3 times 3 is the same thing as 9. Now, I'm not going to prove this in general to you, but it's not very hard to prove if you'd like to figure it out yourself. But the general idea is that if you started off with an even number, and you multiplied it by another even number, the result is always going to be another even number. On the other hand, if you started off with an odd number and multiplied it by another odd number, the result must always be another odd number. Now, if we know that the value a squared is going to be an even number, then as we showed before, the only way you can make an even number is by multiplying two even numbers together. So that forces us to conclude that if a squared is an even number, then a must also be an even number. Now, despite the fact that this doesn't give us the value of a directly, we do know that a has to be an even number, and that's at least something. But if a is going to be an even number, then it must be possible to write it as 2 times some other integer. So how about I write a equals 2 times z, where z is just some random integer. Now, forcing a to equal 2z can be a little bit confusing, so let me explain it with a particular example. For example, we know that the number 14 is an even number, but we can also write 14 as 2 times 7. In this case, a would be the even number, so a is the number 14, and we can write 14 as 2 times z, or in this case 2 times 7, so in this case z is the same thing as 7. But if we know that a is exactly the same thing as 2 times z, then we can go ahead and replace this a over here for 2 times z. Make sure you don't forget your brackets though. So by replacing a for 2z, then we know that 2b squared is the same thing as 2z all squared. Now we can use the index laws to actually distribute this 2 to both of these terms. After this, we can say that 2 squared is the same thing as 4. And then if we just go ahead and divide both sides by 2, then this 2 will disappear, but 4 divided by 2 will just be 2. Now we can apply the exact same shenanigans we applied up here. If the right hand side is going to be equal to 2z squared, then it must be true that the whole right hand side is going to be an even number. But then, if the right hand side is going to be an even number, then the left hand side must also be an even number, so b squared has to be an even number. But then, exactly as we argued over here, if a squared is even, then a must be even, and therefore if b squared is even, then b must also be even. We have already determined that a has to be an even number if this expression is going to be true. We've also shown that b has to be an even number if this expression is going to be true. But then the real question is, which even number do I pick for a, and which even number do I pick for b? Well, regardless of the even numbers that I pick for a and for b, forcing a and b to both be even actually tells us immediately that it's impossible to write the square root of 2 as a over b. To see this, just pick two random even numbers to represent a and b. If you do this, you'll immediately see that you're not going to have the fraction in the simplest form. So for example, if we picked a to be the number 12 and b to be the number 14, then you immediately see that this can be simplified to 6 over 7. This immediately tells us that writing the square root of 2 as a over b is totally impossible, because if the square root of 2 does equal a over b, then a has to be even and b has to be even. But if a and b are even, that contradicts the fact that they are coprime numbers. Two even numbers can never be coprime because they have common factors. They have a common factor of 2. And that means something like 12 over 14 can always be simplified to something like 6 over 7. And these two numbers don't have to be even. In fact, it's impossible for them to both be even. Even if you have a number like 8 over 16, dividing the top by 2 and the bottom by 2 will still give you two even numbers. So you get 4 over 8, and those are both even. But if you do it again, you just end up with 2 over 4, and those are still even. But if you do it one more time, you end up with 1 over 2. And in this case, 1 is not an even number, so therefore it contradicts the idea that you could write this as a over b. So therefore, requiring a to be an even number and b to be an even number immediately contradicts the fact that a and b are two coprime integers, and therefore it must be impossible to write the square root of 2 as a over b. So to read the argument to you one more time, if a and b are both going to be even numbers, then it is totally impossible for them to be coprime. That immediately tells us that this a and b does not exist. It is totally impossible to write the square root of 2 as a over b, where a and b are two integers. So at this point, I'd just like to summarize this lesson. In this lesson, I set out to show you that surds must be irrational numbers. We already saw that you could approximate the square root of 2 with this really long fraction over here, but that doesn't immediately show us that it's irrational, because despite the fact that some fractions can be written with a short period, some other fractions actually have a really long period. We were able to show this by trying to actually write the square root of 2 as a over b, and we tried solving for the values of a and b that make this equation true. Now these values of a and b must share no common factors, and that's actually a really important part of the proof. So the real nail in the coffin here was the fact that we were able to show that a must be an even number and that b also has to be an even number. If both of them are even, then it is totally impossible to write this as a over b. And that should really complete the proof beyond any reasonable doubt that it is totally impossible to write the square root of 2 as a over b, where a and b are two coprime integers. So therefore, if we cannot write the square root of 2 as a over b, we have to conclude that the square root of 2 must not be a rational number. And if it is not a rational number, then we call it an irrational number. And that just about completes my proof that surds are irrational numbers. Keep in mind that I only proved this for the square root of 2, so you may like to prove it for other surds, but in general, it does always hold. And that's something you can show if you'd like to. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.